So 15.2, number 8. So we've got this weird like wheel thing with a spring on it. Right, so here's the wheel. The problem tells you that the wheel has a radius of capital R. It's attached to a wall, and it's going to pivot around, the center of rotation. And then there's this weird spring thing that attaches right here at a radius of little r, right? Okay? So, okay, Joe, you've heard that. All right. So, we're trying to find the spring constant, right? So one of the things we learned, is this where I want to start on this? Yeah. Okay, so for a regular spring, like for a non-torsional spring, we learned that the spring constant is m omega squared, right? Okay, but this is not a regular linear oscillating spring. It's a torsional angular rotating spring, right? So we want to replace this with kappa equals I omega squared, right? Okay, so that means that our omega is going to just be the square root of kappa over I. Agreed? So we need to figure out kappa, we need to figure out I. So figuring out I is actually not too bad. The problem tells you to treat this as a solid hoop of mass m, right? So I is just mr squared. Follow? All right, so now we got to figure out what kappa is. Ugh. So, thoughts about how to find kappa? Kappa, kappa, kappa. Okay, oh, and I'm sorry, this was supposed to be a lowercase letter m. That's a lowercase m. All right, so the problem is, if we were just worried about the spring itself, then it would be true that F is equal to K times X, right? You guys agree with that?
Yes.
Okay, but the problem is, our motion is not about the linear oscillation of the spring, it's about the angular oscillation of the wheel, right? So we've also got this relationship, that torque is equal to kappa times theta, right? Good? All right? So, let me do this. We're almost done, surprisingly. So I need to find a way to relate, to connect all of this. Whoa, fail. It's not what I wanted to do. We need to find a way to connect all of this stuff. Okay? So here's the deal, you guys. I know torque is kappa theta, right? Because it's simple harmonic motion, angularly. All right? What's providing the torque? The spring. So I know two things about my torque. I know torque is the force of the spring times R, and I know that's equal to kappa theta, right? Now, what's the force of the spring? Kx. Oh. So now I've got Kxr equals kappa theta. So now we got to figure out what does that x mean?
Isn't that how far the spring is stretched?
Yeah, it's how far the spring is stretched. Oops. Oh no, what am I doing? This should not be this difficult. Whatever. Okay, so. Seriously? Fail. Darn it. Copy. Paste. All right, so look, you guys, here's the deal. So if I get the smartboard to work, all right, so look, if I stretch the spring through some distance x, then the wheel is going to rotate through some angle theta. What should I be thinking about right now? What group of equations? Those jumper equations, right? Right? Because my x is determined by my theta. Cool? So, jumper equations tell me that x is theta r. Right? Just like v is omega r and a is alpha r, x is theta r. So I'm going to take this orange guy here, and I'm going to go, oh, well, this means, let's see, I'm going to replace x with theta r. So now I've got k theta r squared equals kappa theta. Cancel out the thetas, and kappa is kr squared.
Now K is just regular hook K.
Correct.
Right, so like this equation is correct, or not everything, but if there's a similar problem with this swirl
With this
thing,
configuration,
yeah,
yes. Yeah.
Wait, so I thought torsion pendulums were like this, not like this.
But all of the math that we did will apply to anything that is oscillating in such a way that the torque is proportional to the theta. And our jumper equation shows that that'll be true.
So it works the same. Also, how is the I M capital R squared and not M consistent?
It's the problem tells you to treat the wheel as a hoop.
Yeah, but
And
like-
I for a hoop is mr squared.
But the okay, where's the pivot point? Is the pivot point there?
It's the center of the tire.
Does it say that?
The force from the spring is coming away.
Yes, it did.
Everybody good? All right, so now I think somewhere in this mess of work, yeah, so we just figured out what kappa was. So kappa was, what did we just decide? K r squared. So now I can take these two guys, plug them in up here, and then you have your answer. Cool?
The textbook made it seem much more difficult than that.
The and text, I know, that's why, yeah.
It was like they used some sort of math thing. It was really weird.
All right, good, you guys? All right, anything else from 15.2 that we need to look at? Yeah.
So on number 4, they give you the equation and they have angular frequency in the equation. It's 4.438. And then in B they ask you to find kinetic energy, which is RKE. So you have to use RK equals 1/2 I omega squared, but
Correct.
It's a different omega, right?
Correct. That omega would be d theta dt.
Yeah. Okay.
Make sense?
Yeah, definitely.
Very good.
It's just like a weird thing.
So, what might be easier, let's see.
That's like the.
I'm wondering, I think you can still find, I need to double check this, I think you can still find your elastic potential energy using 1/2 kappa theta squared,
Okay.
and that might be easier because your maximum theta is given to you.
And then just conservation of energy.
Right.
Okay.
That might be easier. Oh, yeah, and in fact, once you find that maximum elastic potential energy,
Yeah.
you automatically know that's equal to your maximum kinetic, right?
Okay. Yeah. Cool.
I think that works.
Yeah.
All right, what else, you guys?
I have a question.
Yeah.
Should we focus on more like deriving equations, or should we focus on
No, and I know I didn't. So here are the things you should be able to derive, and I've gone back on those. And I'm sorry, guys, this being my second year, I'm still kind of figuring this stuff out. The only thing that, from this chapter that you need to be able to derive is the period of the simple pendulum. Other than that, you're good. And in that last chapter, there were 3 things, and they were all on the test. But yeah.
So on the test for
I don't know if I'm going to put it on the test or not, but you should know how to do it. Do you know what I mean? Like, that would be fair game for the test. Follow? Okay? So that is the only derivation from this chapter you're expected to know. Okay? Patrick.
Can you just draw the picture for 7 because I couldn't really visualize it.
No, you're good. I think one of these, there was supposed to be a picture, and the picture got deleted, but it wasn't that one.
It was 3.
It was
Yeah,
3,
that was
okay.
three.
Let's see, number 7. A thin, uniform rod swings about an axis that passes through one end of the rod, and it's perpendicular to the plane of the swing. So that means a thin rod is pivoted at one end. Here's the plane of the swing, and the axis of rotation runs this way. So it's basically just saying it's doing this. All right, and then there's, I think, a disc at the end. Is that right? Oh, no. Yeah, that's it. So it's just this. So it's a physical pendulum. Good? So your I is what, 1/3 n all squared? Everybody good?
Oh, yeah. Is it 1/12? Which one is 1/12?
It's 1/12 if you pivot it at the middle and you use the whole length, then it's 1/12 ml squared. I use 1/3 for anything and just always remember that it's from the end to the pivot point.
Okay, that's it.
Cool?
Yeah.
And again, that's the kind of stuff on a test they have to give you, because you're not expected to memorize all those rotational inertias.
Good, thank you.
Mr. Hacker, for 3, was the cylinder attached to the center, or was it attached to the edge? Because the picture wasn't there.
Yeah, I know. It was meant to be at the end. So the pendulum consists of a uniform disc with a radius yeah. So you've got a rod that's got a length of whatever it is, 50 centimeters, and then there's an additional disc at the end of that. Shoot. Yeah, you're right. I have to picture it. I don't remember. So, but I mean, you find the 2 inertias just by adding them, right? So, okay. Do you guys want to look at any of the multiple choicey stuff from 15 too? What do you got?
I just had a quick question. So, for number 7, like when you're finding like the total like kinetic energy, like you know how far it goes, right? So couldn't you do like the thing that we were doing earlier?
Oh, I'm looking at the wrong number 7. I'm sorry.
So like you find out like how far it goes down, like the difference from like 10 degrees is at the top, and then like 10 degrees is like where it's at, like straight down, and then because you know that it's all kinetic.
Yeah, you could treat so you're saying treat it as a torsional pendulum, right? Is that kind of what you're saying? You know your delta theta. Sorry, say it again.
I was saying, like when we did it in like a previous chapter, we just found, and we did it like energy-wise. Like, could you do it that way still?
Absolutely.
All right.
Absolutely. When you do that, remember to measure your change in
You
GPE.
have to do it from the center.
You do the center of mass, yeah. Yeah. And I think the easier way to do it is once you've got your, maybe you should run through that. Let me see. No, that's the way I did it here too in my notes. Exactly what you said, yeah. Okay, yeah, that works. I think there is a way to do it considering it as potential energy. Once you've got your kappa, weirdly, I think you can write your gravitational potential energy, if you think of it as spring, as 1/2 kappa theta squared.
Oh, and then that's just gonna.
And then that's going to equal your kinetic energy at your bottom. So I think that was the intent behind that. All right, cool. All right, so we get out in 3 minutes, right? So, all right, so we've still got 20 minutes tomorrow.